ಮೊಬೈಲ್ ಬಿಟ್ಟು ಮುಟ್ಬೇ ಬಿಡ ಆನ್ ಮಾಡಿ.
ரெடி ஆயிடுச்சா? அவங்ககிட்ட போச்சேன்னா எங்க கொண்டு போய் கொடுத்தேன்? எவ்வளோ கேட்டேன்? சொல்லுவியே சொல்றோம். ஆமா மேல ஏன் பண்றேன். நீ அவங்ககிட்ட போனா அவன் சும்மாவே ஓட்டிருப்பான். என்ன பேட்டரி கேட்க?
சார் வடிவேல் சார். வடிவேல் சார். வடிவேல் சார். சார். வடிவேல் சார். சார். வடிவேல் சார். Vadivel sir. Vadivel sir.
Sir,
Let me start, sir.
yes, sir. Shall we start, sir? We shall start, sir.
Once again, I welcome all the participants and a distinguished chief guest of Dr. P. Vadivel sir with us. He is served as a senior faculty, Kalberry Academic Ventures, Coimbatore, India. He has completed his PhD in the mechanical area from Anna University in the title of Composite Materials. He achieved 50 plus students projects, 10 plus seminars conducted, 10 plus conference attended through the Calvary Academic Ventures. He published many more papers and patents through his research. So, the valuable resource persons with us. So, I kindly welcome our resource persons, Dr. P. Vadivel sir. The session is yours, please, sir.
Thank you, sir. Thank you for
Yes, sir.
the brief introduction about me. And good evening, everyone. I welcome all to the ATAL program. And let me start my presentation. Sir, is my screen visible to you? Manivel, sir?
Yes, sir. Yes, sir. Is it clear, sir? Audio is clear. Screen also visible, sir.
Okay, sir. Thank you, sir.
Thank you, sir.
Here, the topic of today is investigating the machinability of titanium reinforced aluminum alloys and its performance tool wear and the surface integrity. Okay, so the aim of this investigation is to reduce the weight of the material which we are using day by day. So we know all that the weight of the aircraft or a automobile or a two-wheeler, whatever may be the product we are using for human helpline, the fuel is very much important. So we have to save the fuel. So this investigation supports the weight of the reducing the weight of the object or a material, whatever we focus on it, so that the uh, performance of the automobile or a spacecraft or an aeroplane, whatever may be, is improved. So we have twin advantages. That is, we are increasing the efficiency of that, and also we are reducing the weight of the product. So in those conditions, we can reduce. We are also reducing the price of the product also. So this is the main focus in this investigation. So first of all, we can see the introduction, problem identification, objectives, and the methodology what we have conducted, and the experimental work, and the testing like mechanical properties, wear properties, and machinability studies of hybrid composite using wire EDM. And we have optimized on the wire EDM process parameters, and conclusion and the acknowledgement. So first of all, everyone we know, but a small introduction about the metal matrix composites. So we know that composite material is a combination of two or more dissimilar materials having a prominent interfacing between them. So it is a combination of two or more dissimilar materials. Here we have to focus in the dissimilar materials. So there are different materials. We are combining it into a one part and making the performance output from that. So, and the properties of the resulting material will be superior to the individual material. If we have a aluminium or a steel or whatever may be a single material, individual material, the performance will be very much higher, lower. So we while combining the two or three materials, we are going to improve the material, the performance of the materials improved. So here we have matrix plus reinforcement, that is equal to a composite. We are mixing the matrix material as a having a matrix as a aluminium, and the reinforcement of two materials, two ceramics. Okay, that combining together we form a new composite material. So where we are applying this, the application of this material is in aerospace, automobile, communication, defense, and also in marine engineering. So why we want to go to why we have to go to this new composite material? Because the high strength to weight ratio will be increased. So the strength will be increased when reducing the weight also. And also we have focused on excellent wear resistance properties. We have obtained that wear resistance properties also improved, and high stiffness to weight ratio, and stability at the elevated temperatures. So the material which we have focused is can adapt to all these parameters, like strength to weight, wear resistance, and stiffness, weight ratio, and stability at a minimum temperature, maximum temperature. The particle reinforcement of composites have been reinforcements are added into the matrix to improve the performance, tool wear, and surface integrity of the composites. And also here included the surface integrity, that is surface finish. While machining aluminum or a metal, the surface finishing is a very high challenging for the it is a challenging job in machining aluminum. Okay, so we also included that also. So that the reinforcement particles here we identified that the two materials, two ceramics, that is titanium diboride and boron carbide. So these two ceramics were added in the volume fraction with a less than of 30, and it's been used in the structural and wear resistance applications also. So the particles reinforced with these metal matrix composites offers good mechanical properties. So mechanical properties like tensile strength, wear strength, hardness strength, and brittle strength. So these are all we have focused on this mechanical properties, mechanical area. So then compared to the these are compared with the fiber reinforced metal matrix composites. So again I want to present the application of this MMC metal matrix in a specified components like automotive pistons. The automotive pistons are made of aluminum metal matrices, and it is used in the exhaust guide vanes of in gas turbine engines, and the pistons in the reciprocating of air compressors, and also drive shafts of an automobile, brake drums of cars, bicycle frames, ventral fins, and fuel access cover doors in military aircrafts, the rotating blade sleeves in helicopters. So there are variety, n number of applications are used now. Right now we are using the battery operated cars, so that when when the electric bikes or cars, we can see that the weight is negligibly less when compared to the uh, uh, earlier versions of automobile. So it is very lightweight because of this application of metal matrix, okay, aluminum composite materials. The manufacturing methods for this producing metal matrix composites. How we manufactured this metal matrix composites? Okay, it is by in industry they are using various methods for manufacturing this MMC, like diffusion bonding, powder metallurgy, spray coat deposition method, inch solidification, and also casting processes. So here in this casting process, it is a very simple and economical and feasible method to produce the metal matrix composite. So we have, for simplification of production, we have choose that the casting process. So composite here, how we do the casting process is, the composite is melted and it is poured into the preheated die and to produce the components of a required shape. So in this casting process, we can obtain the shape of the shape by using the dies also. With the help of a die, we can obtain a maximum required size. Okay, so stir casting have been used in the industries. Depends on the type of reinforcement and required properties of casting. So the specifically in casting process, we have chosen the stir casting method. Okay, so in the stir casting method, the reinforcement and properties can be uh, prepared earlier, and it can be used directly in the stir casting process. So this is the schematic diagram of a stir casting setup. So here what we the things using is the electrical motor with a stirrer screw, the reinforcement furnace, crucible, rotor, and the liquid metal. Here the temperature, furnace temperature is maintained at the average of 780 degrees Celsius, and the stirring speed is maintained at 800 rpm, and the stirring time is a maximum of 10 minutes, and the die is preheated with the temperature of 225 degrees Celsius, and the reinforcement preheating temperature is at 300 degrees Celsius. So the preheating of this reinforcement is required, because when compared to the matrix aluminum, that is matrix is aluminum metal, the aluminum material is softer, but the reinforcing ceramics is a very hard material. So there will be some the bonding will not be a proper uh, to improve that bonding. So we have to preheat the reinforced material up to a particular temperature, and it should be maintained for the same temperature for few minutes. So now we come to the machining parts of metal matrix. So the machining of composites can be processed by conventional machining or and a non-conventional machining process also. After preparing of the new metal matrix, and it is machined, the conventional machining and also non-conventional machining process. Here we have used conventional non-conventional machining process, because why we have not going to conventional machining processes? It is lack of machining. Okay, lack of machining, like intricate shapes, profiles, and also hard reinforcement in composites. The cutting, the machining is not feasible in the conventional machining processes. There may be we cannot attain proper shapes or profiles, and sometimes the hard reinforcement will be coming out of the material. So instead of going for conventional machining process, we have chosen the unconventional machining process. That is due to it's because of machining applications, machining complicated shapes, profiles. We can attain maximum of higher accuracy, and the surface finish also will be good when compared to the conventional machining process of metal matrix composites. The problem we have identified, that is the challenging what we had, is the conventional aluminum alloys offer low mechanical properties. Okay, the conventional using the earlier methods, earlier metals like aluminum alloys, what the challenging is, it has low mechanical properties like low hardness, low tensile strength, and also the wear ratio is high. So we have chosen these three mechanical properties: hardness, material properties, and the wear. We have chosen these three areas for focusing this conventional aluminum properties. So the reinforcement in the form of fibers, particles, whiskers are added to improve the mechanical, the wear resistance of the aluminum. Properties of these composites depends on the interface bonding between the matrix and the reinforcement. So the it depends on the bonding between the matrix and the reinforcement. So the many previous researchers, scientists have been reported that weight percentage of reinforcement, that is here we have chosen that titanium diboride and boron carbide, which influences the mechanical properties of casting. So the silk casting process parameters like pouring temperature, the stirrer speed, which improves the mechanical properties of the composite. So these are the parameters which influence the mechanical strength of the aluminum composite, aluminum material, or whatever may be the material may be there. So these three parameters influences maximum influence, so that we have focused on these three. When coming to the wear properties like dry sliding wear parameters, load, velocity, and sliding distance, which influences the wear rate of the material. Hence we have chosen the dry sliding parameters can be and we have chosen the selected dry sliding parameters, and it is optimized for obtaining the minimum wear rate. And when coming to the machining parameters, in the wire EDM, the pulse on time, pulse of time, current, and voltage. So these four parameters influences the maximum metal removal rate and minimum surface roughness in the wire EDM, wire electric discharge machining process. So we have the objectives of the research here. is that to manufacture the metal matrix composite by reinforcing titanium diboride boron carbide in the matrix of aluminum LM13 aluminum alloy by liquid metallurgy route and investigation on microstructure of reinforcement particles. And already we have discussed that material properties like hardness, tensile strength, and ductility, with varying the percentage of titanium diboride and boron carbide, and also tribological properties like the wear property. We are going to focus on this research. And also we have chosen the reinforcement of titanium diboride with 10 weight percentage, and boron carbide is of up to 5 weight percentage, and investigate the effect of process parameters like pulse on time, pulse of time, current, and voltage in wire EDM. The optimize the wire electrical discharge machining process parameters for obtaining maximum metal removal rate and minimum surface roughness of the aluminum LM13 aluminum alloy based on the composite hybrid composites. So here, this is the research methodology chart for how chart with the LM13 aluminum alloy, boron carbide. That is, in general, we call it as ceramics. So here, first we prepare the metal matrix of matrix of aluminum LM13 aluminum alloy, and we have melted the aluminum alloy, and the reinforcement were preheated, and it is added to the LM13 aluminum alloy. And after that, we have prepared the composite melt using the strip casting process with a varying weight percentage of 0 to 10 weight percentage of titanium diboride and 5 weight percentage of boron carbide. So after the mixing is done, the manufacturing of aluminum alloy have been done. Then after that, the hybrid composite is analyzed for microstructure, hardness, tensile test, and wear test. So these specimens were prepared to the standards, and the standard with the standard specimens we have undergone the microstructure, hardness, and other tests also. Then after that, we have characterize the composites microstructure, hardness, tensile wear, and the examination of fracture surface and the wound surfaces. Here we have this chart explains the how the machining process of the machining process in wire EDM process parameters have been done. After obtaining the new hybrid composite material, the specimen has been prepared for the standard wire EDM machine, and we have selected the parameters, chosen the parameter values also according to the machine. Wire EDM machine, we have chosen the pulse on time, pulse of time, current, and voltage. Then after doing that, the DOE, design of experiments using RSM, response surface methodology, has been done. Then machining of composite as per the experimental design, and measuring response, and namely the metal remove rate and the surface roughness. Perform, we have done the analysis of variance and developing the regression analysis of ANOVA by using ANOVA table, and developed the regression equation for the material removal rate and the surface roughness. Then finally, we optimize the wire EDM process parameters for higher metal removal rate and the minimum surface roughness value. Like what we have done it in the two stages. One is for one is we have prepared the new hybrid material and investigated the material properties, and the another one is we have done the uh, machining process parameters, and we have identified the metal removal rate and the minimum surface roughness. So the work plan, what we have done. So in manufacturing, we have done the aluminum alloy with the boron. We have mixed the aluminum matrix and the composite materials by using the stir casting process, and investigated the mechanical properties of this new hybrid composite by using stir casting process, and studied the on the biological behavior of the LM13 aluminum alloy and the titanium diboride and the boron carbide particulate by stir casting. The machinability studies of aluminum alloy with a particulate hybrid composite by using wire electrical discharge machining. For optimization, we have done the electrical discharge of the machining process by using higher metal removal rate and the minimum surface roughness of LM13 alloy and the titanium diboride particulate using hybrid composites. So here we come to the experimental work. How the manufacturing of this LM13 aluminum alloy, boron carbide, titanium diboride is done. So first of all, we had the matrix and aluminum alloy, okay, and then the weight percentage of titanium boride is obtained with a 0 to 10 weight percentage, and with a constant 5 percentage of boron carbide is kept and been prepared by using the stir casting process. Here we have varied the percentage of titanium boride from 0 to 10, and we had constant 5 percentage of weight of the boron carbide for this process. The hybrid composites prepared using stir casting setups consist of an electrical induction furnace with a melting capacity of 700 degrees Celsius, and a stainless steel crucible with a melt capacity of 2 kg. Okay, the electrical furnace, the aluminum metal is melted by using electrical induction furnace with has capacity. The capacity of this induction furnace is about nearly 1500 degrees Celsius. Here we have chosen at the temperature of 780. The aluminum is melted and it is kept for a few minutes with this 0 to 5 minutes uh, in the furnace, and then it is stirred. The electrical with using the electric stirrer, the with a stirring speed of 800 rpm. The optimum range of this electric stirrer is we have selected by using various experiments. We have because if the rpm which is selected, the speed of the motor stirrer is selected below this, in a number of trials we have conducted, the below this rpm, what we attained is the mixing of the matrix and the stirrer is not proper way. So there forms some the dispersion of this ceramics is not proper. So in the another trial we have increased this speed of the stirrer up to 900 rpm. So at that period of time, what we obtained is the metal inside the crucible is maximum coming out. So this is not the metal which is it forms like a foam inside the induction furnace. So we then after number of 5 to 10 trial we have conducted, we conducted more than 10 trials by varying this electric stirrer speed, because this is the challenging job in this stir casting process. Because if the safety is not safety should be maintained while using this stirrer speed, because it may injure the person who is operating the electric stirrer. So so this finding this optimum value of the stirrer speed is very crucial, and it's we have done many number of trials with very safety precautions. And the cylindrical die, we have chosen the cylindrical die because why we choose the cylindrical die made up of die steel, because it will be useful for machining the hybrid material. So that there are some other researchers have they had that rectangular shape or a square shape material, but we have chosen the cylindrical die because for machining this aluminum material, the cylindrical die is very much helpful in machining. So we have chosen the cylindrical die. The aluminum alloy is melted in the furnace, and the reinforcement are preheated to 300 degrees Celsius. The preheating of reinforcement is very important, because if the matrix aluminum metal is in very hot temperature, the reinforcement is not preheated, means the bonding between the aluminum material and the reinforcement are not good. So the first trial what we had now, we didn't have the preheated is not done for the first two and three trial experiments. So at that time what we identified is the bonding between the aluminum and the titanium diboride and boron carbide, no, there is no bonding, there is no proper bonding. So it breaks like a brittle. So the material is coming out, the titanium diboride, no, that is not fully mixing with the aluminum alloy. So after preheating, number of the seventh trial, at the time of seventh trial, we have used that preheated material. So the bonding is very good between the aluminum and the reinforcement material. So after preheating this to this 300 degrees Celsius, the reinforcement is slowly added to the melt, and it is stirred with the speed of 800 degrees Celsius, 800 rpm. So the compound materials, the preheated temperature of 225, and also important thing, the die is also preheated. Die is also preheated up to a temperature of 225 degrees Celsius. Here the die is preheated, reinforcement also preheated. So these are all the main parameter, the main things we should be focused in this work. So the casting which we produced is about 300 length and 30 diameter material. So after that, the microstructure, density, hardness, tensile strength, and ductility of this hybrid composite has been investigated. And also the tribological properties of composites have been examined on the pin on disc wear testing machine. So the wear test of the machine material is done using the pin on disc apparatus. The one surface, no, the one surface of the wear test specimen have been analyzed. One surface, the machined surface is analyzed by using the SEM. The wire electric discharge machining process parameters have been optimized. The process parameters are pulse on time. It is mentioned as T on, and the pulse off time, T off, and the peak current, that is denoted as IP, and the servo volt, SV, are selected to optimize the process by using the RSM, response surface methodology. So these are the parameters in the wire EDM machines used for optimization. The LM13 aluminum alloy reinforced with 10 percentage, the 10 weight percentage of titanium biboride, and 5 weight percentage of boron carbide composites for the maximum metal removal rate and the minimum surface roughness have been analyzed. So we have chosen the 10 weight. These are these 2 percentage, no, weight percentage of 10 and 5. These are the maximum weight percentage of this ceramics. So this is used for analysis of MRR and minimum surface roughness. So here first we have selected the tested the element, aluminum, pure aluminum, no, we have before manufacturing these hybrid composites, the LM13 aluminum alloy reinforced with uh, before that, before processing this, starting the work, we have tested using this FEM, SEM analysis, field emission scanning electron microscope, the elements which are present in the LM13 aluminum alloy. So the weight percentage which are present in the, like, weight percentages are given here. The elements which are present in the LM13 aluminum alloys are silicon, manganese, copper, iron, titanium, chromium, nickel, manganese, and the other balances are others are aluminum. Balance is aluminum. So the properties, these properties of this aluminum alloy is it is a lightweight material, because of its low density. It has good strength and does not behave brittle at low temperatures. It has the machinability of this material aluminum, and used to machine the process. It has high coefficient of linear expansion, and it has a good thermal and electrical conductivity, and it has good corrosion resistance, and also it has good malleable properties and metal joining processes. So because with these parameters, with these advantages, we have chosen the LM13 aluminum alloy for our work. So the physical properties of the aluminum LM13 aluminum alloy is it has the density of 2.7, and the melting point of this melting point is 295 degrees Celsius, and the modulus of elasticity in megapascal, it is 73 megapascal. Ultimate tensile strength is 572 megapascal. The Poisson's ratio is 0.33, and the fatigue strength of the LM13 aluminum alloy is 159 megapascal, and the yield strength is 503 megapascal. And the physical properties of the boron carbide, the ceramic we have used is the boron carbide. Why we have selected this boron carbide is because of its property, extreme hardness, and it is difficult to mold to high relative densities, while not the utilization of sintering aids. It's a good chemical resistance, and also good nuclear properties, and with low density. So because of this very important properties, we have chosen the boron carbide. So the property and the values are listed here: the density, melting point, hardness, fracture toughness, Young's modulus, electrical conductivity, thermal conductivity, thermal expansion, thermal neutron capture, cross section. So with all these property values, we have selected the boron carbide, and this is listed of list of property of titanium diboride. Okay, this is because impact resistance is armor. The titanium diboride, no, the it is used as resistant in armors and cutting tools, crucibles, like nucleon absorbers, and the wear resistant coatings. So these are all because of these advantages, like very good properties, we have chosen the titanium diboride. So the picture you are here you are seeing is the stir casting machine. Okay, furnace, melting furnace temperature with 780 degrees Celsius. The stirring speed with a maximum of 800 rpm. The stirring time is 10 minutes. And the preheating temperature of this ceramic system, 300 degrees Celsius. Preheat temperature of the mold is 220 degrees Celsius. So this is the stir casting setup we have used for the experiment. Okay, this is the, here you can see this is the stirrer, and this is the casing, and the preheating the mold is preheating the furnace. Mold is preheated with the muffle furnace, and it is molded in the machine. And this is the muffle furnace used for preheating the die, also the uh, ceramic particles. And this is the testing equipment which is used to computer aided image analyzer, and this is the Brinell harness tester, and this is the universal testing machine used for testing the hardness of the material, and this is the beer testing apparatus. So this is the pinned on disk apparatus. So here this level attachment for applying dead weight. So dead weight will be applied here, and the panel control is here, and the specimen is fixed. The specimen is of round diameter, with the specimen is a round specimen, so that it can to fix it, it can be fixed in the specimen fixer. So this is a counter steel disc. So in the disc only the specimen is rotated, and the electric motor is here, electric motor which is used to rotate the disc. And this is the field emission scanning electron microscope for testing the SEM images. And this is the wire electrical discharge machining we have used for our machining processes. So in the certain discussion, we have the varying percentage of this aluminum alloys. Okay, here in the left side you can see the LM13 aluminum, that is pure aluminum bar, pure aluminum, and here LM13 with a 5 weight percentage of boron carbide. Okay, then in the third line it is shown that LM13 with a 2.5 weight percentage of TiB2 and 5 weight percentage of boron carbide. And the fourth one is LM13 with 5 TiB2 and 5 B4C. And the last one is 10 TiB2 and 5 boron carbide. And the weight percentage of titanium diboride is 0 to 10. And the weight percentage of boron carbide is 0 to 5. See here, already we have discussed that the boron carbide is kept constant in all the levels, and we have varied the weight percentage of titanium diboride. Okay, and here the hardness of the material. The hardness of the material is 82 BHN, 98 BHN, 106 BHN, and 126 BHN. And the next one is ultimate tensile strength of the obtained material is 121 megapascal, 138 megapascal, 151 megapascal, and 174 megapascal. And the percentage, finally, the percentage of elongation is 11, 9.2, 9, and 8.1. So these are all the mechanical properties we obtained by varying the weight percentage of the reinforcements. So these are the specimens we have used for the microstructure. See the n number of 1 to 8 numbers we have samples were prepared for the study of microstructure. So in the microstructure you can see the titanium diboride and boron carbide were uniformly dispersed in the aluminum. The first picture which is shown is A. The picture A is the pure aluminum LM13 aluminum alloy with the dispersed. Here, the microstructure of LM13 aluminum alloy. In the picture B, you can see that titanium diboride and boron carbide. See this is the particle which is which has shown as in the red mark, that is titanium diboride and boron carbide. So this is the attributed to the high stirring speed which produces vortex during the process of composites. The particles the particles are distributed throughout the material. So the microstructure study reveals that the dispersion, the mixing of the aluminum matrix and the reinforcement is uniform all over throughout the matrix. So to confirm that to confirm this mixing or dispersion, we have done the microstructure study for several samples. And the samples prepared for hardness test. So already told that the Brinell hardness test has been done for that. So these are the specimens with varying diameters. For the microstructure, the specimen is very small, and for the hardness testing, the sample is a little bigger than the then with the this is the hardness test. The improvement for the it is compared with the LM13 pure aluminum, LM13 only the aluminum material, and the new hybrid composite material. It is compared with the weight of reinforcements in the TiB2 and boron carbide. So in the x-axis you can see that the weight percentage of boron carbide ceramics, and in the y-axis you can see the Brinell hardness numbers. It is starting from 62 maximum of 130 BHN, and the weight percentage of titanium diboride ceramics is 0 to 15. So totally we have these two, and the results from the testing of hardness test, we have plotted that in the scale. Okay, then after that it is the maximum hardness of composite increased with 126 BHN with the weight percentage, with the increasing the weight percentage of reinforcement. So the plot shows this the variation in the improvement manner of 126 BHN of with the increasing of reinforcements. And the next one is we have done the tensile test of the. These are the tensile specimens which are done for the tensile test. While plotting the tensile strength, we have reinforcement in X and the tensile strength in megapascal. The test results shows that the maximum strength of 174 megapascal is observed for composites containing 10 weight percentage of titanium diboride and 5 percentage of boron carbide. So the maximum ceramic part, the maximum weight percentage of the ceramics has the high tensile strength of what we obtained is 174 megapascal. In the result, when compared to the earlier one, the result is improved with the ultimate tensile strength of 53 percentage when compared to the LM13 aluminum alloy. So this is a very good result which we obtained after n number of iterations. And now coming to the fracture surface, the hybrid composites. Here you can see this is the micro pore holes between of crack nucleating points. So in this fracture, the fracture surface is obtained by same result. You can see some dimples. So you can see dimples in the sense there are some valleys. Okay, dimples are shown here, so that this is like if we example, if we break a chalk piece, okay, the cross section of the area you can will be not in the uniform. There will be some holes or projections will be there. So that is the part here. So we can see the dimples here. The hybrid composites had dimples on the surfaces. This is the better interface bonding between the matrix and the reinforcements. So because of this dimples, it is confirmed that there is a better bonding between the matrix and the reinforcement. So the micro pores, between the matrix and the reinforcement as a crack nucleating point. So, and the crack is propagated towards the particle agglomeration regions, which results in the fracture of the composites. So, because of this micro pores, the crack is initiated at some point, and it tends to break the sample. So the agglomeration of the particle in fracture surface, which had voids between the matrix and the reinforcement. So the agglomeration of the particles, the fracture surface, no, it will had some voids between voids in between the matrix and the materials. So this picture shows the dimple, dimple in the sense it is like a hollow. This is called shown as a dimple in the arrowhead, and the TiB2 is placed here, and boron carbide is placed here. So this shows that in some particular regions, all the ceramics are placed evenly distributed. So this picture shows that only. See the agglomeration. See in this picture, the agglomeration, that is a mixing of material and the ceramics is shown. So because of this agglomeration, the crack may be initiated. So now we are coming to the dry sliding wear properties. So effect of the sliding distance. So the sliding distance is done. The wear test is done with a sliding distance of 2000 meter under a constant load of 20 Newton. So here the graph shows, the graph in the x-axis the sliding distance is noted, and in y-axis the weight loss in milligrams is noted. See here a number of the compositions were plotted. So with the distance of 2000 meter with a constant load of 20 Newton is plotted here. The weight loss of these samples increased with the increasing sliding distance of from 0 to 2000. See in the x-axis it is denoted that 0 to 2000 with a load of 0, 10, 20, 30 and 40 milligrams in weight loss. So the weight loss decreased up to 67% by adding 10 weight percentage of TiB2 and 5 weight percentage of boron carbide. So for the in this material, the weight loss wearing is done. Wearing it also has wearing, and also the weight loss is stopped at some particular point. So after that, the weight loss is very negligible. The samples, these are the samples which are prepared for the wear test. In the dry sliding wear properties, the wear rate, this is the sliding distance. The graph shows that the graph is plotted between the wear rate and the sliding distance. The wear rate of samples against the sliding distance is plotted, and the wear rate decreases with the increase in sliding distance from 0 to 2000 meter. The wear rate of the composites has been decreasing with the increasing the weight percentage of reinforcement in LM13 aluminum alloy, and the minimum wear rate of is 0.0068 milligram per meter is observed in the study. And the next one is coefficient of the plot is between the coefficient of friction and the sliding distance. So the coefficient of friction is decreased with increasing the sliding distance. So when we increase the sliding distance, the coefficient of friction, so we know the value of friction in the where is the friction value of friction in brakings and brake drum, the friction between the brake drum and the brake shoe. So without friction, the brake will not be stopped, the vehicle will not be stopped. So for that purpose we have undergone this friction study. So coefficient of friction, the average coefficient of friction we obtained is with 15 weight percentage of reinforced composites, and matrix is 0.39 and 0.312 respectively. And the next one is cumulative weight loss of the specimen and the load. The graph is plotted between the weight loss and the load. The cumulative weight loss of the matrix and the hybrid composite against the load is given here. The cumulative weight loss of composites decreased with increasing the weight of reinforcement. So cumulative weight loss is decreased with the increasing the weight percentage of reinforcement, so that the cumulative weight loss decreased by up to 58% of reinforcement. So in this study, zero weight percentage of TiB2 and zero weight percentage of boron carbide, that is only LM13 aluminum alloy is used to done wear test is done on the pure LM13 aluminum alloy. So here you can see the continuous grooves and delamination of this LM13 aluminum alloy. So one surface of this matrix which gives the continuous grooves. You can see here continuous grooves like one by one next to that, so that on the surface parallel to the sliding direction. So sliding direction and the delamination. So delamination and the continuous grooves is observed in regions. And this is only with the 5% of boron carbide. So here you can see the shallow grooves in the sliding test, wear test. In the wear test of this 5% of boron carbide gives that shallow grooves in each places. This is the next level, which is 2.58% of titanium diboride and 58% of boron carbide. See here, you can see that debris and the shallow grooves is observed here. The one surface of this 2.5% of titanium diboride and 5% of boron carbide, which reveals the continuous grooves and shallow grooves. So on the parallel surface to the sliding direction. And the next one is 10% of titanium diboride and 5% of boron carbide. So here you can see that fine grooves on the surfaces, and it is maybe attributed to high hardness of composites, which decreases the weight loss as observed during the wear test. So you can see the fine grooves here. Okay, you can see the fine grooves. And the next one is 10% of titanium boride and 5% of boron carbide. The one surface. So one surface of this specimen with 10 and 15 weight percentage of fine grooves as compared to the other composites. When comparing to the previous testers and with this the final one, the grooves are very smooth. The fine grooves which gives in the sliding direction of the material, so this gives good result. That is, fine grooves is observed in the final level. And with the load test, this is the FESM of load with the 20 Newton of load is applied on the specimen. And the next one is 30 kilonewton load is applied on the wear test apparatus, so that we obtain the shallow grooves. And in the when we apply 40 Newton of load, we observed that there are deep continuous grooves, and delamination is also noted here. And with the load of 50 Newton in this test, the delamination is maximum when we had a load of 50 Newton. So the reveals deep grooves, and with the delamination is also observed in the most of the regions. The composite tested at a lower load shows fine grooves, and delamination is also predominant at higher loads. And now we come to the machinability studies of this hybrid composites, that aluminum alloy and titanium diboride and boron carbide, by using the wire electrical discharge machine. And this is the picture of the wire iridium. And here the process parameters. These are the machining process parameters and their levels. Here the process parameters are voltage, current, pulse on time, and the pulse of time. These are the process parameters within the units, and these are the levels. We have chosen the levels from 1 to 5. Okay, so these are the process parameters and their levels. These ranges are selected by doing some trial experiments, and the maximum possible ranges are chosen based on the technical specifications of the EDM, by electrical discharge machining. So with these two, we have taken the parameters and their levels. In the metal removal rate is the weight of the metal removed per unit time during EDM process. So in the increase in the peak current and pulse on time increases the metal removed. So when we increase the peak current and pulse is on at the time, the metal removal rate is high. The metal removal rate is directly proportional to the product of energy transferred per pulse frequency, and hence the increase in peak current increases the MRR of the composite. Okay, so the experiment is done using the central composite design. The experiment DY is done using the experimental design using RSM. Response surface methodology. In this, the central composite design is chosen. So here the run order is fixed from 1 to 30, and the pulse on time and the pulse of time, current and voltage. So with this pulse off and pulse on time, the result is obtained. And this is the chart for weight percentage of 5 weight percentage of titanium dioxide and 10 weight percentage of boron carbide using wire radium. So these are the metal removal rate. So this is ANOVA table. The ANOVA table gives the result as a significant. The model sum of squares, degrees of freedom, mean square F value, and P value. The R squared value what we obtained is 0.9746, and the adjusted R square value is 0.9508 value. So this is optimum result we have obtained. The analysis of variance of metal removal rate of composite in this model, the chance of this 1.45 percentage, that is lack of it, occurs due to the noise. The R square value of the value is 0.9746 in the observed for the MRR, and this model is significant and fits with the actual experiment results. The model shows the lesser difference between the actual and the predicted data. Here the ANOVA table for metal removal rate MRR of a composite is the pulse on time, voltage and current. So with these parameters, this increases significantly, influences the MRR of the aluminum with the maximum, the level 5. So the terms have p values is less than 0.05. The parameters which influence the metal removal rate are the parameters like pulse of time, pulse on time and pulse of time, pulse on time and current, time and voltage, pulse of time and current, and pulse of time and voltage. So and square of pulse on time, square of pulse of time, square of current. So these are all the parameters which influences the MRR of the metal removal rate of the composite, hybrid composite. So this is the result for a regression equation for MRR is predicted for the metal removal rate is 10 weight percentage of TiB2 particulate hybrid composite, and MRR is we find here is 0.427 plus T on plus I on the equation can be used for the MRR of the hybrid composite. So a metal removal rate by using the iridium is the predicted MRR and the actual MRR. The actual MRR is the results which we obtained from the VR testing machine, and the predicted MRR is the result which we obtained from the software. So the variation of the predicted and actual removal rate is shown plotted in the graph. The MRR is predicted using mathematical equation, and it is compared with the actual metal removal rate. So you can see that both the values are close to each other, and hence the slope is almost 45 degree. So you can see the slope is here, and the predicted values and the actual MRR is plotted so that it is close to the inclined line. So here you can see the result. This is the response surface plot for MRR with a constant function of pulse on time and pulse off time for a constant current of 180 amps and voltage of 20. So here you can see this graph which shows which is plotted between the metal removal rate and T on and T off. So this gives which is giving the increasing pulse on time increases the MRR of the composite. So it can be noticed that the generation of spark during the pulse on time which increases the metal removal rate. See, when the pulse is on, at the time the voltage, the spark during the switching on time, that increases the metal removal rate. So the next is the variation of 54 pulse off time and voltage of 20 volts. So here you can see that current is the plot is between the current T on and MRR. So you can see that increasing pulse on time slightly. When we increase the pulse on time, the metal removal rate of the composites. So metal removal rate increases drastically at the higher level of current. When the current is increased, you can see here, when the current is increased, the metal removal rate is drastically increases. So this is due to the heat generated when the increase the current, which increases the metal removal rate of the samples. So the current influences the maximum part in the metal removal rate. So here this is chart is for 54 ms and 180 amps of current. So here you can also see that increasing the voltage, when we increase the voltage, the metal removal rate is increased. Application of voltage which increases the metal removal rate of samples. And the next plot is with 112 ms and voltage of 20 volts. So here when the plot is between the current and T off, in this T off conditions, the pulse of time decreases the metal removal rate. When the pulse is off, it decreases the metal removal rate. So this is due to absence of spark between the wire and the workpiece. So the spark influences the metal removal rate drastically. And this is the plot between the voltage T off and MRR. So while increasing the voltage, the metal removal rate and the pulse of time, as increasing the pulse of time decreases the metal removal rate. When we increasing the voltage and we switch off the pulse, the metal removal rate is decreases. And here the next one is the variation of MRR with the voltage and current. So the plot is between the voltage and current. The increasing in the voltage and the current increases the metal removal rate. And this is the surface roughness tester used for our work. Mito SJ210 make tester was used. After the machining of the components, surface roughness of each workpiece is tested by placing it on over the surface table. And this is the surface roughness chart with the hybrid composite. And this is the ANOVA table for surface roughness of the composites. Here the squared value is 0.9817 and the adjusted R square is 0.96. The analysis of variance test the results of the surface stiffness. And this model, there's a chance of 18.22 percentage, that is a lack of it occurs due to the noise, and the R square value or R square value of 0.9817 are observed for the surface stiffness. And the model, it is significant and fits with the actual experimental result. To obtain the model shows that the lesser difference between the actual and the predicted data. So here the regression equation is developed. So the regression equation for the surface roughness is developed to predict the surface roughness. The surface roughness in the sense the smooth, how long it is smoothed or it has the surface is rough. So the aluminum 13 alloy reinforced with the 5 weight percentage of boron carbide and 10 weight percentage of titanium diboride particulate of hybrid composite has the predicted the surface roughness. The surface roughness equations are used to do the shown equation. No, the surface roughness equation is used to predict the metal removal rate of the hybrid composites. Seeing the surface, the graph shows this. The graph is plotted between the comparison of predicted and actual surface roughness of hybrid composite. So in the x-axis you can see the actual surface roughness, which is measured by using the surface tester machine, and in the y-axis the shows that predicted surface roughness of the material. So here the surface roughness of the composite is predicted using the mathematical equation and compared with the actual surface roughness. It can be seen that the both values, the predicted and the actual surfaceness, are very much closer to the slope, and the slope is equal to 1. Hence we can confirm that the equation is well predicted and the surface roughness of the aluminum based hybrid is good. And the next one is the plot is a variation of the surface roughness with the increasing pulse on time and the pulse off time. So you can see that constant of 180 amps and the 20 voltage. So the increasing in pulse on time increases the surface roughness at all levels of pulse off time. So this is due to the generation of spark during the pulse on time, which increases the surface roughness of the samples. Also increasing the pulse off time decreases the surface roughness. The previous slides which we have seen the similar graph now, that is for surface roughness, okay, surface finish, and this is for surface roughness of the samples. So here the variation of the surface roughness with the increasing pulse on time and current. So it is can be seen that increasing pulse on time and current, with the increase of the current, the surface roughness is done due to the heat generator while increasing the current. So because of this current, the metal removal rate in the result is increased with the surface roughness. The increase in current increases the surface roughness of the composite material. So here this is the graph between the current and with the variation of the surface roughness with the current and the pulse of time. Okay, while increasing the pulse of time up to 52 milliseconds decreases the surface roughness of the sample, and the further increase in pulse of time increases the surface roughness. So this is due to absence of spark in between the wire and the workpiece during the pulse of time, so which decreases the surface roughness. And this is the plot of variation of surface roughness with the voltage and pulse of time. So here it is notice that the increasing in voltage See here, the increasing in voltage improves the surface roughness of the composite at all the levels when the pulse is off. So while increasing the pulse of time decreases the surface roughness of the samples. And the next one is variation of surface roughness with voltage and current. See here in the standing, this is surface roughness, voltage and current. The increasing the voltage and current significantly increases the surface roughness. So this is due to enormous heat generated between the pulse and the workpiece. So the application of this voltage and the current increases the surface roughness. And in the in the conclusion, we come to the conclusion part, that the microstructure result shows that the uniform distribution of the reinforcement and minimum level of porosity in the composites. The hardness, the mechanical properties like hardness with the increasing content of this reinforcement, the maximum hardness of 126 BHN is obtained or observed for the composites. The tensile strength, no, the tensile strength is increased by the addition of reinforcement with the ceramics. So maximum tensile strength is obtained is 174 megapascal with the weight observed for 10 weight percentage of TiB2 and 5 weight percentage of boron carbide. The tensile strength of the composite increases in an amount of 53 percentage in the composites than the unreinforced composite material. When come to the fracture surface of the matrix, shows the dimples on the surfaces, so that the crack was observed at the interface of the matrix, and the reinforcement with the dimples are observed for the hybrid composites. And the next one is the weight loss. When coming to the weight loss of the samples, increased with the increasing load and the sliding distance. The average coefficient of friction for matrix and LM13 to 10 weight percentage and 5 weight percentage of boron carbide is 0.39 and 0.312 respectively. So the cumulative weight loss is decreased up to 58 percentage, and the reinforcement of 10 weight percentage and a 5 weight percentage. The worn surface has continuous grooves on the surface, and the sliding direction, along the sliding direction, and the delamination is observed in the most of the regions. Fine grooves are observed for composites as the lower loads, and delamination for the higher loads. And the ANOVA table, ANOVA result shows that pulse on time, voltage, and current significantly influences the metal removal rate. So the mathematical equation which is developed for the prediction of the metal removal rate is R square and adjacent R square are very close to each other, and this equation will give the MRR with the excellent accuracy. So while increasing the pulse on increasing the pulse on time increases the MRR, okay, due to the generation of spark between the material and the material. The material removal rate is increased at the all levels due to the higher amount of heat generated due to the application of voltage and the metal removal rate of the composites. So when comparing to the increasing current increases the MRR of the material, and pulse of time increases the increasing the pulse of time decreases the metal removal rate of the samples. So the pulse on time what we obtained is 0.109.5 microseconds, and the pulse of time is 55.12 ms milliseconds are found to be the optimum process parameters of the current of with 161.37 amps, and the voltage is of 10.41 volt, so which offers higher material removal rate. So these are the optimized value we obtained here. And when coming to the surface roughness, okay, when the coming to the surface roughness, the parameters like voltage, pulse on, pulse off, square of pulse on time, square off time, which gives the maximum of hybrid composites. While increasing when the increasing the pulse on time increases the surface roughness of the composite of all the levels due to generation of spark during the pulse on time, which increases the surface roughness of the samples. So with the increasing pulse on time and current, uh, the heat due to the heat generation between the lowest surface. And here I conclude my uh, presentation, and the session is open to queries. If you have any doubts or for clarification, I am waiting for your questions.
Thank you, sir. Thank you for your deep and pleasant explanations. Dear participants, please ask your queries with the resource person.
If there is any no queries, we can have.
Sir, there is one questions in the chat box.
Okay, sir. Let me.
Can I read it, sir, or can you get it from there, sir?
Sir, please read it, sir.
Which is any particular name for latest stirrer casting machine? Which is any particular name for latest stirrer casting machine?
Sir, there is no particular name or specifications, because for the stir casting machines, it is manufactured according to their requirement. It is a like there is no standard. The volume of the casting which is produced, no, that may differ according to the foundries. For a small scale foundry, the size of the machine will be minimum, and for the large scale industries, the size of the specification of the machine is higher. So there is no particular standard name or design for stir casting machines, sir. So it vary according to their requirement.
Thank you, sir. One more question. What is
Yes,
the
sir.
size of particles used? I think he's asked about your research presentation side.
Okay, sir. The size of particles.
Particles.
Let me come to the slide, sir. So the particle size.
Is asking about reinforcement particle size.
Oh, okay, sir. I'm getting that. The size is of magnitude with a 1.0x, sir.
Thank you, sir. Any other questions from participation side? Sir, one more questions is there.
Yes, sir.
Whether the results of regression analysis can be used to formulate multi-objective optimization problem.
Yes, sir. It can be done, sir.
The same person's Dr. Sabarinath asking, what is the difference between pulse on time and pulse off time?
Okay, sir. In the wire EDM machine, it is the working principle of wire EDM machine. So when the current is passed through the wire, the spark will be generated in between the wire and the material, the work specimen. So when when the current is on, the spark generated between the between the gap of the wire and the material. So when we switch on the current, the spark produces and it removes the material. So when we switch off it, the spark will not be generated between these two. So this influences the metal removal rate and the surface roughness of the material, sir. So it will be it's like alternate current. The once automatically it will be switching on, switch it off, so that the pulse will be pushed around pushed continuously for the machining process in the wire EDM. So that is the term we mean it as pulse on and pulse off. If the pulse is on, the spark is generated and the material is removed. If the pulse is off, the material is not removed.
Thank you, sir.
This is Dr. N. Gopalswamy, sir.
Yes, sir.
Am I audible?
Yes, sir.
Thank you very much for your wonderful presentation. I think
Thank
you
you,
have
sir.
given more slides. Oh, is
Yes.
actually how you have done all those things.
Yes,
It's a
sir.
wonderful presentation. And
Thank
further,
you, sir.
this you have given some titanium diporide, LM13. LM13 nothing but aluminum.
Yes, sir.
Yeah, plus
Which,
boron carbide. Is there
yes,
any
sir.
particular specific ratio for this for producing composite material?
Yes, sir. It is previously it is mentioned in the slides. No, sir. There is a weight percentage of the weight percentage of LM13 aluminum and weight percentage of titanium diboride and weight percentage of boron carbide, sir. So we are using the measuring the weight with a particular weight percentages added to the materials.
So based on the weight ratio only you are adding. Okay.
Yes, sir. Yes, sir.
In this titanium boride, it's around 2,100 Vickers on us.
Okay, sir.
And this LM13 is 105 Vickers.
Yes, sir.
Okay, what is the your this thing? What is final your product that is composite materials on us in Vickers?
Because it is I have placed this.
You are given somewhere in BHN. I think I have seen it.
Yes, sir.
BHN, you have given it. Yeah.
Yes, sir. We have done in the harness material 126 BHN, sir.
Yeah, BHN you have given.
Yes, sir. Yes, sir.
Where any applications where we are going to use or any suggestions from you?
Sir, actually, we tried for the automobile in the automobile engine part. We trying for implementing it in the automobile engineering part, sir.
Okay. More wear and tear. That is.
Yes, sir. The wear and tear parts, and also for the ships, sir, we are mostly focusing for the ship engines, so that there is a usage of engines, no, sir.
Okay. Thank you very much. Thank you all the best. Thank you.
Thank you, sir. Thank you so much.
Thank you, sir. Dear participants, please switch on your camera for the photo sessions.
Sir,
participants are requested to switch on your camera.
Sir, I want to thank you, Dr. C. Manivel, sir, Professor, NPR College of Engineering and Technology, and Mr. Professor M. Prakash, NPR College of Technology. Thank you for your guidance and support, sir.
Thank you, sir. Thank you, participants. Sir, from your presentations, we got taken away points about the deep investigations techniques of the machinability of titanium reinforced aluminum alloy and optimizations of wire EDM process parameter for hybrid composites. We hope that all participants and including myself, we taken away of important output parameters and the selection of parameters to improve the machinability and optimized wire EDM parameters and hybrid composite performance of to achieve the surface integrity of the particular materials, which is suitable for the applications of aerospace, automotive, and defense industry. Thank you very much for your wonderful presentation, sir. Thank you.
Thank you, sir.
Participants, the both sessions feedback link is available in the chat box. Please fill it.